I'm Marlon Shannab and I'm going to talk about hyperbolic metamaterial-based photonic devices. Here we have a general overview of what I'm going to show you. Regarding the research context, we want to develop a technology that can exploit the quantum optics properties. Indeed, such devices can be applied in different fields, such as quantum computing, quantum communication, in particular for the quantum key distribution, and also in the biosensing applications. In order to develop such devices, in the last years the single photon sources have been studied, and we want to couple these kind of sources with the hyperbolic metamaterials, that are so called because of their isofrequency surface that is related to their dispersion relation. Indeed, this particular surface leads to an enhancement of the density of the states and therefore to an enhancement of the emission. Moreover, with these hyperbolic metamaterials, we can control the emission spectrum intensity and also the direction of the emission. In particular, these metamaterials can work at room temperature. Here I've reported the possible ways to implement and develop these hyperbolic metamaterials. In this moment, we want to increase the intensity of the emission from the single photon sources without losing this particular behavior. Indeed, this is one of the typical issues related to this kind of sources that usually have a low emission rate. Here I also reported the issues related to specific kind of single photon sources. Indeed, regarding the quantum dots, they can work only at low temperatures, while for the color centers in the diamond, for example, we have a strong photonic coupling that leads to a broadband emission. Unfortunately, we have also some issues related to the hyperbolic metamaterials. Indeed, we have some difficulties in the theoretical descriptions and also in the outcoupling of the surface modes. In order to analyze these problems, I have worked on simulations and also on the optical characterization of an emitter placed above a multilayer structure. In particular, regarding the simulations, I have computed the near-field and far-field behavior and also estimated the Purcell factor. That is a way to estimate the enhancement of the emission related to the coupling with the hyperbolic metamaterial. While regarding the optical characterization, I've improved the optical setup in order to have a better fluorescence analysis that consisted in the backfocal plane measurements and also on the fluorescence spectra and imaging. Here we can see the achieved goals concerning the simulations. In particular, I've calculated the Purcell factor in different configurations and also simulated the control of the direction of the emission when a grating is placed above our metamaterial. In particular, here in figure C, we can see that we can obtain an almost perpendicular emission. Regarding the achieved goals related to the optical characterization, we observed the enhancement of the emission from an emitter placed above an outcoupling grating, as we can see here on the figure, and with the setup improvements, I made it possible to pass very easily from the image plane to the backfocal plane. Finally, here I've reported the next steps we want to take. Indeed, we want to quantify the actual Purcell factor with lifetime measurements in order to compare it with the simulated one. We want also to acquire more measurements about the outcoupling in order to optimize this process, and after that we want to take all these optical measurements on single photon sources. In addition, we want also to realize and design new photonic structures exploiting the self-assembled block copolymers. Indeed, with these copolymers we can create particular structures as the lamellic structures, as we can see here on the figure. Structures that are realized with the collaboration of the INRIM Institute.